All right. Good afternoon, everyone. My name is Derreck Coleman, and today I'll be telling you all how I helped improve the Large Underground Xenon, or LUX, dark matter detector. Does anyone recognize this painting? Yeah. It's Van Gogh's Starry Night. So, a little background to tell you why we think dark matter even exists. There's this phenomenon known as gravitational lensing, where Einstein figured out with the advent of special relativity that mass out there in the universe can actually bend light, because mass bends space-time. And so if you had an object like a quasar far away and some huge amount of mass like a galaxy in the way, then the light would be bent around this galaxy, and when it comes to us would appear to be coming from two different locations. So it's with this that we can perform all kinds of analyses on the images that we see with our telescopes. So this is a very famous, very important picture. This guy down here is Franz Zwicky. And back in 2006, he discovered what's known as the bullet cluster. And what we see here is two clusters of galaxies passing each other. Now, all the matter that we do know about and we can see with our telescopes, and we have ever encountered in the universe, most of it just smashed into the matter from the other cluster and annihilated on impact. Well, not annihilated exactly, but exploded into a dust. And we see that ionized gas here in pink. Now, this is all the matter that we do know about, but using that gravitational lensing I talked about a moment ago, we're able to detect that a large majority of the total matter in these clusters passed right on through the other cluster without interacting at all. Now, this is a big problem because all the matter we know about should have interacted in some way, whether the electromagnetic force or the strong nuclear force, but it just passed right on by. And so we knew that something was out there, and it's something that we've never seen before. So we started asking questions like, well, if there is this invisible matter, where is it? It turns out it's everywhere. Here's another image of a cluster of galaxies and the mass. All these little spikes are the galaxies themselves, where there's a huge concentration of mass. But you can see there's this hill going through the whole cluster. This represents the large majority of the matter, again, diffuse throughout the entire cluster and not concentrated in any one place. This is another strong piece of evidence for the existence of dark matter. And last, it's known as the galaxy rotation problem. Now, imagine a galaxy spinning. It's a lot like water in a drain, where in the middle, you would think that the galaxies would be spinning with a much higher velocity. And as you go further away, just like the water in a drain goes slower, the galaxies in this cluster would be going slower, because they're further away from the total mass, and the gravity is a little weaker. That's what you would expect to see shown here with this blue dotted line. However, what we actually see is this red line, that as you go further out from the middle of the cluster, the velocity is basically the same. And that's crazy. And it shows us that as you go further out from the middle, these galaxies are still seeing more and more mass. And it's kind of like on a turntable, where a point, even as you go further out, it isn't slowing down at all. That's not exactly true, because on a turntable, the further out you go, the higher your velocity is. But it's to give you a sense that things aren't slowing down like we thought they would be. So how much dark matter is there? Turns out about 4 times as much as the total normal visible matter that we're used to and have detected so far. So what is it? Well, so far we know that dark matter is heavy or massive, and it doesn't interact via the electromagnetic or strong forces, so we call it dark, and it's left over from the Big Bang. Well, fortunately, supersymmetry theory predicts the existence of something called a neutralino, and it has all the right traits. And so we call these weakly interacting massive particles WIMPs, and they're exactly what we're looking for. And just for the record, there's plenty of other dark matter candidates that it could be, like machos and other things from different theories. But how can you find something you can't see? So the analogy I give you is if you're fumbling around in a room with no lights on, looking for your car keys, how can you find them? Really? you would try and touch them. You would try and run into them directly with your hands and not see them with light. Confucius once said, "The hardest thing of all is to find a black cat in a dark room, especially if there's no cat." Well, that's the idea behind the large underground xenon detector. We take this detector, we put it a mile deep in an old gold mine in South Dakota. And the reason we put it deep underground is to filter out noise, all kinds of solar radiation, cell phone signals, even cars passing by shaking the ground. We want to filter out as much of this as we can because this background noise is going to get in the way of detecting the very quiet dark matter particle. So here's how it basically works. Here's our detector sitting in some purified water, even more shielding. And if a dark matter particle came on by, there's a chance that it would run straight into a nucleus of some of our liquid xenons shown here. And the liquid xenon is chilled to minus 700 degrees Fahrenheit. It's pretty cold. It's 772 pounds of it. That's a lot of it. And it's all sitting there, not moving, barely at all, waiting for something to hit. Things like neutrons could hit it, gamma rays, but what we really want to see is that wind. So it'll come in, smack into the nucleus. And when that happens, light comes off. And these things on the bottom, these photomultiplier tubes, or PMTs, are basically cameras. The light would go to the bottom and the top, and we would see a flash. And that's the first flash. But what also happens is electrons are released from the xenon, and they'll float right to the top because of an electric field. And when the electrons get up to this gassy xenon up here, there will be a second flash. And with those two flashes together, we're trying to figure out where the event happened in the detector. Why do we want to know where it was? Because all the noise happens on the sides, basically. And if we can find an isolated event in the middle, we can say with great certainty that it could be dark matter. So how do we test that? Well, we run computer simulations. It's called Monte Carlo. And so here's an example of LUX. It's a really sophisticated Monte Carlo simulation that's been developed by the entire LUX collaboration. It's like 17 universities. And so what's shown here is the empty detector with no events. And let's say, for an example, a neutron came on by with about 10 kiloelectron volts of energy. Now, it would impact somewhere around here and release a lot of light. And that light would bounce around the sides of the cylinder until it was collected at the top or bottom. Well, this visual helps you get a sense of what's going on, but it doesn't actually tell you anything. To know what's going on, we need to take that raw data coming out of the detector and do some analysis. So we get our signal from the PMTs, and we run a position reconstruction to figure out where it was. If we can do that position reconstruction with better accuracy, we can more accurately report our discoveries when we publish. So to give you an idea of what the position reconstruction does, let's do a simple example. If you had a Gaussian curve, and this represents the probability an event is going to happen at a certain position, and you sample this thing a number of times. If you sample it a bunch of times, say 1,000 events, you're going to get a distribution that looks a lot like what you'd expect, the original function. But the problem is, if you only sample it a few times, then what you get might look completely different, or not at all like what you started with. And that's the problem we're encountering here with LUX, is that a dark matter signal is inherently low light. There's not much data. And so it's really hard to get that position reconstruction. For example, if we think an event happened over at the side of the tank, our error is so great, we say, oh, it happened at the side, maybe in the middle. It's just horrible. But if we can say it was in the middle, probably in the middle, then that's good enough for us. So, the whole goal here is to increase the sensitivity of our detectors by making the detectors bigger and by making our analysis better. So before us was an experiment called Xenon 100. It set the sensitivity this low. We're hoping to set it even lower. And afterwards, LUX and another collaboration called Zeppelin are going to get together and make the LZ project. So what's next for us? Well, this year's run is going to be published later this year. That's exciting. But even better, next year we're going to start a whole year-long run and get the best data we can out of LUX. But then, if that's as good as we can do, where do we go from there? Well, how about something even bigger? So LZ is going to be the exact same idea, this two-phase xenon detector, but scaled up by about 10 times. That'll get us even better results. So what have we learned? We can only see about 20% of the matter in the universe. Something called dark matter makes it the other 80%. We hope it's a WIMP particle. And that the quality of our findings depends on our equipment and our data analysis algorithms that I help with. A detector like ours is sensitive and it's scalable, which means the next project will be easy to make. We really want to thank the Jacobson group, particularly Tristan is here, Victor who's here, Professor Jacobson couldn't make it today, for all their help. I truly could not have done any of this without all of you. I need it. Leah Carroll and Nathan Sheep for all of their help preparing for the program and practicing, and the SURF program and the Rose Hills Foundation for their absolutely generous help. Here's a picture overhead of South Dakota on site taken by Vic himself. There's the old gold mine story. Any questions? Yes.
So why do you